All right, welcome everyone. My name is Nina and I'm from Hyperganic to present you today something really exciting. Before we go on, let's watch a short clip that just went live on LinkedIn. Somehow the audio doesn't come, but never mind. All right, so we finished up with a very interesting question, what's next? And today I would like to talk about physics-driven generative design. And maybe we can get a quick peek on what the future of engineering could look like, and especially what we imagine it in Hyperganic to be. But before that, I'd like to introduce myself, because I think I see many new faces that I never spoke in this audience before. My name is Nina, and I finished my PhD in Technical University of Munich. That's where everything started with investigation of additive manufactured structures. In particular, I'm a computational engineer by training, so I'm also a software engineer. And what we had to do is develop new numerical methods that could digest the complexity of additive manufacturing. In the beginning, it was just a PhD. I never thought that we are going to have a startup, but my colleagues and I together founded DfAM. That was a company that brought these numerical methods actually to the commercial world. And last year, Hyperganic acquired this company, and we embarked on this journey all together to build something really important. So it's been already a year, and that's how we started. And before this, I'd like to say how I, together with my colleagues, saw Hyperganic. Before this, Hyperganic was about algorithmic engineering. We always talked about a paradigm shift. And why so? Well, basically, we all learned how to design in CAD, how to design with these surface-based designs. I tell you my experience. In this case, I spent hours on designing something like what you see on the screen. Algorithmic engineering was something completely different. We took a motto and saying engineers will never have to solve the problem twice. Why? Let's encode this knowledge. Let's put it in terms of the code in something that can be easily automated, easily repeated without an engineer touching anything on their computer. And this allowed Hyperganic actually to focus on something else. Engineers are trained to solve problems. I ended up in front of the computer trying to fix and learn the new tool instead of actually solving an engineering problem. That's what was for me algorithmic engineering and what it was all about when we joined. Moreover, Hyperganic was not just algorithmic engineering. I already talked about the concept, but this was extremely fast. I really was surprised. I really have to admit it, because when, as a software engineer, you think, oh, how did they do this? And when I speak about speed, I speak about two things. I speak about the speed of the kernel, about the computation, and visualization. I never thought that voxel-based models with sign distance fields can be visualized on my laptop without any lag. That's when I talk about speed, and it brought so much flexibility, because you could design something that you never thought before, and it could have been complex, it could have been simple, it doesn't really matter. You just need to put your imagination and start designing efficiently. But you know what? I have to say that the acquisition was actually for a reason. This was not enough. This was a design. And I think I will speak to everyone in this audience that every chair that you're sitting on has a purpose. You're sitting on it. Every cup for coffee has also its purpose. You put something hot in it and you don't want to burn. Physics was missing. Physics was something that gives the design a purpose for later. And that's how we came to be. But I actually never spoke about why such an acquisition. You can tell me, intelligent analysis exists already. I agree, I studied it myself. The thing is, when you talk about such complexity, I think meshing is quite a problem. I think I can challenge you to, every one of you, to just mesh the objects from before. So in DfAM, we developed a technology that has no meshing at all. It's a quasi-meshless method called finite cell method that allowed to eliminate this meshing process. And guess what? It allowed to come from a design to simulation with one algorithm. There was no any more setup. There was no any more tweaking. This also allowed us to perform simulation on something like CT scans, point clouds, flawed STLs, just even static CAD models. It doesn't really matter. That's what this technology was really capable of. And we went on, and the first challenge that we had to achieve when joining Hyperganic is to embed and make it work together like one. So 1+1, design of Hyperganic and simulation of DfAM. We achieved it, and we also had a little bit of discussions because we also heard, oh, you need to introduce assemblies. So as of now, you can run linear elastic analysis on homogeneous and non-homogeneous material loss. And when I speak about non-homogeneous material loss, it's something that comes from CT scan where every point is really different material. You can also simulate different assemblies, and it's absolutely geometric agnostic. And the first question that I get asked very, very often, yeah, cool, new method, how fast is this? Because of course, this is not really black magic. I'll answer this question right now. So this was actually, the publication was accepted today, so you can all go and read it on. This was done together with ETH, and we were working on development of auxetic materials with Hyperganic core. This ran within 30 seconds on this laptop. That's the speed we are talking about. It's rather simple. I will never claim that large objects will never take time, but that just gives you an example or an anchoring point where we stand. The next question is how accurate it is. Physics actually requires accuracy. I brought an example with the colleagues, and this is comparing to Nastra. At the left, you see actually our code. At the right, you see Nastra of very simple geometry. It was just because we actually had a lot of conversations about it. We can confidently claim that our method converges in the same rate as finite element method and to the same values. We also have quality control. We also have exactly the same troublesome convergence process, but we converge to the correct values. And because we are coming from the PhD world, we can say that please go ahead and read our publications, and you'll see that we actually spend quite some time on validating and seeing whether the math is correct. But this is still also not enough, because when we were faced with Hyperganic geometries, nothing is linear elastic. Nothing is actually structural. There are quite a lot of other applications. So we went ahead and we had to face and implement thermal simulation, heat conduction, new physics. So we went, instead of going depth, we went to the breadth of the physics possible. So you again can simulate multiple domains and see which law you would like to choose. Still not enough. Next step was to implement electromagnetic-statics, and this we released in the past November of last year in our platform. Of course, we are not imagining it's one-way coupling. Electromagnetic coil analysis is possible, but it's electromagnetic statics. And again, I need to repeat that there was a mind shift of company. For us, it was important to deliver accurate results that are robust and have no step in between design and simulation. And I remember in the past year when I joined, in my education, I studied structures. I often got asked, okay, but we want to do these fluid simulations. I was like, all right, yeah, sure. Never heard of it, and I don't really know how to do it, but we actually had to sit down and do it. And as of now, I can proudly say that we had to challenge ourselves to find a new discretization method that would allow to work on Hyperganic core and enable CFD simulations. We have already implemented the flow models with boundary conditions and straightened curve boundaries. And as of now, as we speak, we are introducing advection conversion support such that we can comprehensively simulate thermal fluid dynamic simulations and guess what without meshing. That was a challenge that we had to complete, and we are still on the way of delivering this to the public. So all in all, simulation took a very, very big step. Inside Hyperganic, you can save this manual effort, and instead of focusing on meshing and trying to see where the surface is reconstructed well or not, whether it's watertight, focus on actually what matters, solving your workflow in different physics, advanced, accurate, and fast. Well, you would say, yeah, good, still not enough. For me, this is not enough, because we spoke quite a lot during this morning that there are very siloed steps. There's design, there's simulation, there's production. Usually, I very much agree these teams never talk to each other. The designers are just there with their cubicles. Simulation guys really don't talk to designers. And guess what? This really slows down the process. This slows down the production of products that actually could matter. It can take years. We asked actually one of our customers how long it takes, and they told me 5 years. I was like, cool, that's kind of a lifetime for me. But imagine actually the world that these siloed steps would not exist. Imagine that they would merge together in a seamless feedback loop without anyone touching the computer. That was the next challenge. And that's what we are currently embarking on, and you already see what is possible. That's actually what for me means physics-driven generative design. This is the first step towards it. And in order to really say again on accuracy and what it will achieve, we can go on and see, for example, this is just an aluminum ring, and we talked about the heat sink application, so we wanted to really position our boundary conditions right and see where it is going to lead us. Well, there were 6 total iterations with 30 validations, and we achieved 59% increase in total heat dissipation. There was no one sitting in front of the computer while this was happening. It was 30 minutes. So as I said, we don't do black magic. We still need some time, but this is fully automatic. And this is exactly what opens up a whole world of generative design, because this is optimization. There is nothing in there more than what we talked about before. But for me, generative design is exploring the whole design space without any interaction, where you can actually see how the objects can look like and maybe have different trade-offs of costs, of manufacturability, of performance, and so on and so forth. This is where we have to arrive. And for this, we still need something else. It is still not enough. And I must admit that it will never be enough for the PhD people inside Hyperganic. But you know, last year we had the platform launch. And everyone knows that this Hyperganic was a platform that was fully based on coding. We got a lot of feedback. And I must say that it was quite challenging, but we learned something very important. No matter the software tool, we are all humans. And we are all absolutely different. As I said, for me, software engineering is just to my heart. I can code, I can program, and this is what I would choose when I have to solve an engineering problem. However, I'm so sure that there are people in this audience who would choose UI, and it's totally fine. So I would like to ask a question, and it's more a rhetorical question inside for you. How long did it take you in your past jobs or in the current job to enter and understand the software, to become productive? Just answer it for yourself. I'll just tell you my experience, which doesn't need to be necessarily true. It takes me ages, although I'm an engineer, although I really understand what I have to do. Because there's tons of buttons, there are tons of, some are programming tools, some are buttons somewhere else. It slows us down. So we learned that the tool has to be human-centric. We learned that we all are different and we all need different tools to achieve the same goal. And that's okay. And in the past year, I told you, we were a coding platform. That's of course gives quite a lot of flexibility, especially if you know how to code. You can just go crazy and generate these kind of pictures in terms of minutes. But we have introduced the UI such that you can easily get into our platform. Moreover, since then we brought it to the web to make it accessible for you, such that you can just go on and try it for yourself without any further installations. You see here there is a missing piece. There is a very big piece missing because there is something that we learned from being kids. We learn language. So therefore, you should be able to talk. To talk to your tool without any further interaction and be able to solve your problem. And that's what Hyperganic has been working on for quite some time. We all have heard today too that their artificial intelligence is on the rise. For me, this is a very big thing. You know, I know deep learning, machine learning, and AI for me is something big. But the thing is that ChatGPT and other tools showed us what is possible. But I think it's also possible in engineering, where the tool can be made accessible, where the tool can become creative. And I already see quite confused faces. I'll tell you one more motto of Hyperganic. Instead of talk, show. And show what is possible, and see where you are, be accurate, be humble, and show to the world what else we can do and what we cannot do. So I will invite you on a journey to finally unveil Hyperganic, because we had a lot of comments about this too. So I had to record this demo, and I'll start it, and I'll tell you one more thing. This is not sped up. This is real time. So we go to our website, and instead of just clicking on the UI that you can see up there, this is really just a prototype. You can go inside your text-to-3D and try to generate objects. So here I wrote that I would like to create a cylinder with an outer radius and an inner radius. Also, forgive me, so you already hear me speaking, I forget articles. I'm from different language, and I also can mistype things. But guess what? We are confident that this can be produced. And one more thing. With Hyperganic, we are sure that the objects that are produced are watertight and engineering ready. So there is no more this kind of, point clouds where you would see that there are holes inside the object. There is a real cylinder that are produced, but you would tell me that cylinders. You also cylinders. Well, as simulation engineers, they actually like cubes because that's a perfect benchmark for all of the tests. But instead of this, let's really infill it with some pattern. Simple. Euroid pattern. I put some cell sizes and some wall thickness. Maybe it will help me to do something else. Well, the tool is not magic. I also promised you this. This is an MVP. And this is really happening real time. There is no GPU based. It's really all CPU, and you get your cylinder out with all Generative patterns. And I promise you yet another time, you can export it to actually one 3MF as of recently weeks. And you can just go on and try to manufacture them. Still not enough. Let's try to, instead of just infilling it with a pattern, transition it radially to another pattern, something like a Fisher code in this case. You can also control how fast, but in this case, notice that what I'm writing inside is not really precise. I just said transition to physical. So it will produce something, and you need to be very careful with what you're doing. If you really want to be precise, you can put transition width and see how it is. And you already see it on the screen, right? So you see that the pattern is transitioning already to the right side without me yet another time clicking on something else. But still, let's try to, you would say, yeah, it sounds quite small, right? Let's change the radius. Let's go to 25 millimeters. And while we are waiting, and no, this is happening on this laptop, yet another time, instead of this, there is now a connection to the web. And there is just a CPU node running with 8 CPUs. No magic, there is no GPU. And the visualization is live. There is no acceleration, there is no caching. And of course, you already see that it takes longer, and we can produce just a simple cylinder. So this is what new Hyperganic is. This is what we've been developing for quite some time, and we really believe that this will be the future of engineering. Because each one of us is different. People will still be able to code here. You can go on the browser, open the code workspace, and just go crazy with that. You can also go for UI, you can go for talking, and the objects will be produced. So that's what we believe in Hyperganic is a small peek in the future. And now I need to show you this video. I urge you to go to LinkedIn because there is unfortunately a very is useful with the new Hyperganic, with the new platform. And we've been building it for quite some time. So actually today is a very important day for us. And instead of just ending on this note, I'd like to invite you to scan this QR code and just apply for our exclusive private video release, where we will talk openly about our products, where you will be able to test it yourself, because this is a time where we need your help. We need your help to improve our tools further. We have heard you before in our software platform. Now we build something else, but still, you are the people who are doing the future of engineering. And we would like to thank you to being with us in this journey and continuing with us further. Thank you very much. And if you want to see this software live, come back to me. It's on my laptop. Thank you.